Good afternoon. I'm Dr. Joseph, and here we are back doing some calculus. So we're starting Unit 2 now, which is applications of derivatives. So you've learned what they are and how to work with them. Now we're going to see what can they do, what can they help us to do. So today is mean value theorem and Rolle's theorem. So I'm just going to read the theorem at first, and then we'll unpack it a bit. Let f of x be a function that is continuous on the closed interval AB and differentiable on the open interval AB. Then there exists a point C in AB such that f prime of C is equal to f of B minus f of A over B minus A. So I want to say a couple things before doing any examples. This fraction on the right here, this is the average rate of change for our function over the interval AB. F prime of C is the instantaneous rate of change for f of x at x equals C. So this theorem is saying that if these hypotheses are satisfied, then there is an actual point on that interval where the instantaneous rate of change equals the average rate of change. So let's unpack these hypotheses a tiny bit. So one thing to point out is that being differentiable at a point implies being continuous at that point. That was something we mentioned a while ago. So differentiable on the open interval from AB implies that you're continuous on the open interval from AB. So if you check differentiability over the open interval, you've already checked continuity over the open interval, but you still need to check it because there's a difference between this and this. So we still need to check that you're continuous at the two endpoints. So you need to be right continuous at the left endpoint, A, and you also need to be left continuous at the right endpoint, which is B. So let's draw a little picture. So maybe this is f of A, and this is f of B. Ooh. And my function's just doing what it's doing in between there. So to check that we're right continuous at A, we need to check that the limit of f of x as x approaches A from the right is equal to f of A. And then to check that we're left continuous at B, we need to know that the limit as x approaches B from the left is equal to f of B. So if I check those three things, then that's equivalent to checking what's written here. And in practice, that's generally just sort of a more direct way to go about it. So we need to check that you're differentiable on the interior points, and then you're continuous as we approach the two endpoints. So this is just a graph, and it appears to be a cubic polynomial. It looks like it's differentiable everywhere. So let's just see, what does this jargon actually mean on a particular actual interval? So I'm gonna say that's a point I can recognize, and that's a point I can recognize. So this is like 1 minus 4 and 5, 4. So I'm going to investigate the interval 1 comma 5. There are many possible intervals you could look at here. That's just one where it's easy for me to tell what the y values are. And by looking at the picture, we're pretty convinced that f is continuous on 1, 5 and differentiable on the open interval 1, 5. So the MVT tells me there exists an x value c in 1, 5, so it's in between 1 and 5, where f prime of c is equal to f of 5 minus f of 1 over 5 minus 1. So that's 4 minus negative 4 is 8 over 4, so equal to 2. Now remember that 2, I should think of that as my average rate of change over 1, 5. And you can also think of it as, because it is, the slope of this straight line in between those 2 points. Okay, so looking at the picture, let's try to guess where this point is. So it should be a point where the derivative f prime of c is equal to that average rate of change. So it's going to be a point where the tangent line is parallel to that blue line that I just drew. So maybe right here is one, and looks like there's another one right around there. So in this case, there are 2 possible values of c. So this is an existence theorem. It just says there's at least one. There could be many, but it tells us there must be at least one point with this property in that interval. Okay, let's see an example. So before I read this, many of you have probably been through a toll booth where you take a ticket when you enter and it has a timestamp. And then when you exit this certain portion of highway, you have to give them the ticket and they know how far it is between the 2 toll booths and they have a timestamp on there so they can tell your average speed. And if your average speed was higher than the speed limit, they can give you a speeding ticket because they know you must have been speeding. So that's kind of a real life occurrence of the mean value theorem. And it probably seems just like common sense when you say it like that. And it should seem like common sense, but that's kind of a good thing that calculus is proving something we believe in our souls to be true. So this says, suppose you're driving a car. After an hour of driving, you've gone 55 miles. So that tells me my average speed was 55 miles an hour. Can you guarantee there was a time during the drive where you were going exactly 45 miles an hour? What about 60 or 55? So I'm going to answer these in reverse order. So 55, yes, there must have been, because that's what the mean value theorem tells us. 1 second. Okay, so what about 60 miles an hour? This we don't know. Or in other words, no, we cannot guarantee. There was a time we were going 60 miles an hour because we could have been going 55 the whole time, for example. Never went any faster than 55. Um, what about 45 miles an hour? So here's where there's like potentially a question about if you know that you started from zero from rest, then yeah, you would have had to get you would have had to gone 55 at some point, which we already said. So then if you started at zero, then you would have at some point had to be going 45 by the intermediate value theorem. Um, but the way this is written, I'm not really sure. Maybe we've been driving for 8 hours already and we were going 55 when we started. So in that case, um, it's it's certainly possible if we could have been driving already when we started the timer that we were going 55 miles an hour the entire time, right? So in that case, no. Um, so th that will be more clear if we ever asked you it on a quiz, but that's kind of a good thing to think about is did you start from rest or not? Okay, so example two, suppose that a company's stock prices in dollars are modeled by the function S of t whenever t is larger than one. Um, show that there's a time c in this interval where the company's stock prices are neither increasing nor decreasing. And just for some realism, one second. Pi over 2 is approximately 1.57, and 3 pi over 2 is approximately 4.71, just for frame of reference. This function says that it's only valid when t is greater than 1, so we're certainly in that range. Now, what do we want to show? We want to show there's a time c in that interval where the stock prices are neither increasing nor decreasing. So if the rate of change is 0, that means f prime of or s prime of t c is equal to 0. That's our goal is to show that there's a time c where s prime of c is equal to 0. And if we're going to try to do this using the mean value theorem, then that s prime of c should hopefully be the average rate of change over some interval AB, where f is differentiable and continuous and all that. So we need to check a couple of things. Since we have this goal in mind of finding a point where the derivative equals 0, I'm going to first check out if this interval even makes sense to be attacking this with. So if 0 is equal to this average rate of change here, we could multiply both sides by b minus a and get that 0 equals s of b minus s of a, and then add s of a over to say that the y values at these two endpoints should be the same. And that makes sense because then the line between them is horizontal, so its average rate of change is 0. Okay, so The endpoints are giving me the average rate of change that I want, but I still need to check those hypotheses about differentiability and continuity. So first, let's just see what is S prime of t. So I'm going to use the quotient rule here. So low d high minus high d low over low squared plus 0 for the 2. And that is t sine t minus cosine t over t squared. So we know that t is a polynomial and sine t and cosine t are trig functions that are continuous everywhere. So everything in the numerator is continuous on all real numbers. And then we're dividing by t squared. So this exists wherever t is not equal to 0. So that means that S of t is differentiable on the interval 3 pi over 2, pi over 2, 3 pi over 2. Now, we said we should check that it's continuous from the right at pi over 2. Well, I'm going to be a little bit lazy and say this is even differentiable on 0 infinity. So that means it's differentiable from the right and the left at the two endpoints, which means it's continuous at the two endpoints. And so then it's also continuous from the right and the left. So if you can check that it's differentiable even past the endpoints, then you don't have to do this other check about continuity. But you could also check that separately. So I'm just going to write it down. Limit of S of t as t approaches pi over 2 from the right is equal to S of pi over 2. And limit as we approach 3 pi over 2 from the left is equal to S of 3 pi over 2. So that means all the hypotheses are satisfied. And so MVT guarantees a C value in that interval where S prime of C is equal to 0. That doesn't tell me what it is, but it tells me that it exists. All right. So here's a try it yourself problem. Company's profits are modeled by this function P of T, where time is measured in years and profits measured in millions of dollars. So there's a time between year 2 and year 6 where the company's profit is increasing at a rate of $261,000 per year. So give that a try. And the last little bit of this video is talking about Rolle's theorem, which we actually just did an example of. And this is just the mean value theorem again. So compare this to this. They're like the eye doctor. Rolle's theorem says we have the same hypotheses. We've got some interval AB. We're continuous on the closed interval, differentiable on the open interval. Now the last sentence is different. If f of A is equal to f of B, then there's a point C in the interior such that f prime of C is equal to 0. So this statement is a special case of MVT where the average rate of change is equal to 0. So you might wonder, why do we have a special name for it? And the reason is that this is actually how you prove the mean value theorem. You first prove Rolle's theorem, and then the mean value theorem is Rolle's theorem sideways. So this is just sort of an easier statement to apply calculus to, and I can give a very quick explanation of how that goes. So if this is our value k, which is both f of a and f of b, it means we have these 2 points on our graph, and we have a differentiable function in between these 2 points, and we're trying to assert that there must be a point C where the derivative equals 0. So the proof is basically, if the function starts off by increasing, well, it must eventually decrease to get down to that point. And so there has to be a point where the derivative is 0. If it started by decreasing, it would eventually have to increase, and you'd have a point where the derivative is 0. And if it doesn't increase or decrease, then it's just a straight constant function, and the derivative is 0 at every single point. So that's the idea of how the proof goes. And then mean value theorem is a very simple twist on that, just to make it slanty instead of flat. Great, so that's all for today, and see you next time.